All right, this is day number 3. In my opinion, this is the most difficult thing that I teach all year in any of my classes. So if it seems a little rough for you, just get with me and I'll see what I can do to help out. All right, we already know this first slide. We know that with a series, that S in red is the perfect answer. That's if you added the entire series all the way to infinity, spent your whole life adding, which of course nobody's going to do. The blue is the nth partial sum. Let's say you added the first 8 terms together and you got sick of it and you're like, I'm done. That would be S8. If you subtract them, that's the error, because the error is basically the perfect answer minus what you did, which will give you the rest of it that you left off, also called the remainder. And the error, as we learned in section 9.5, also called the Lagrange error, is always less than or equal to the first neglected term, which is a sub n plus 1. So in other words, let's say that we did add the first 8 of them together. That'd be, S8. The first neglected term then would be term number 9. So we've left off term 9, term 10, term 11, and so forth and so on. We know that the difference between the first 8 when we add and the perfect answer is going to be less than or equal to that term number 9. Okay, so that should be old knowledge. The good news is, since this line of thinking works with series, it also works with functions. So let's say that we have f of x. Let's say we're trying to find sine of x. And we know what the graph of sine of x looks like. It's a beautiful curvy sinusoid between 1 and -1. It flows perfectly. But a graphing calculator cannot calculate sine or cosine or a tangent, believe it or not. You can't anticipate everything a user might type in. Who knows if a little kid's going to type in sine of 1, 2, 3, 4, 5, 8. Maybe they'll skip a couple digits. How do you write a program that would be ready for that? Well, you don't. Instead, you have to use Taylor polynomials and Taylor series. So let's say that this was the perfect sine of x right here. What we would do is we would just take the sine of x that we've been building the last 2 days, something from the memorized sheet. Maybe we would go out 5 terms, maybe 7, and that would be our approximation. And then everything else in green would be what we blew off. So let's say we did go out to the first 7 terms. We're like, hey, 7th degree Taylor polynomial for sine of x. Then we chopped off the rest starting with term 8. This remainder polynomial, even though it starts with the 8th power, we still call it r sub 7. So I don't want to confuse you guys. The first neglected term is 8th power, but it's the 7th degree remainder polynomial. And that's because we were working over here in blue and we chopped it off after 7. So this, the name of this, I should say, is based on that. All right, if we want to know what the remainder is, just simply take the perfect answer, subtract off what we got, which is the error, by the way. That's how close we were to the perfect red answer. That ends up being the same thing as the remainder. The error is the stuff we neglected. Kind of makes sense. All right, so this also works for functions. So good, good, good. Now we're about to get a little crazy. Here's Brooke Taylor's theorem, the famous mathematician from England. He said if a function f is differentiable through order n plus 1, in other words, you have as many derivatives as you need, there's not suddenly a corner or a cusp or anything like that, and you're in an interval I that contains c. All right. Then for each x in this interval I, there exists this letter called z. Z is between x and c such that that is true. I took the box in the book, copied it, and made some notations in different colors. That's my writing. I tried to match the font there. That statement is true where the green rectangle, the remainder polynomial of nth degree, is equal to, oh boy, Now you look back at the green rectangle down there in the lower left corner. The remainder polynomial, nth degree, is equal to the n plus first derivative of f evaluated at z of x minus c, remember a function centered at c, to the n plus 1 power over n plus 1 factorial. Oh my gosh. I have to figure out how to make this make sense to you guys, and that's what I'm going to do today. It'll take several slides, I'll make analogies, I'll color code everything, but we're going to make it work. All right, so in other words, if our polynomial approximation in blue here goes out to n terms, and after a while we get tired, we're like, we're done. We stop after we do the nth power, the nth derivative, nth factorial, then it makes sense that here in green, the thing that I left off, the very first term that I left off, would have n plus 1s in its exponent, in its derivative, and in its factorial. So, okay, I get that. Everybody's been centered at c the whole way. You get your minus c's. So it's not surprising that the first neglected term would have also had the minus c there, because you're centered at c. The only thing that's weird is I don't exactly get what this z thing is, and we have to talk about that. It says there exists z between x and c such that this produces the desired effect. All right, let's go to our next slide, and I'll try to make this make sense. Okay, as you can see, they took the factorial and they kind of lumped it into the front to make it part of the coefficient, and that's fine. It doesn't have an x in it, so it can be out there. I personally like to put the factorial below everything, but it means the same thing, so I'm cool. We do know that that part of the Taylor polynomial does involve a derivative, specifically in the numerator. That's an n plus first derivative of f of x, evaluated at z. Okay, so there's a derivative embedded in there. Great. Taylor's theorem says there exists this weird z somewhere between x and c. We can make z anything I want. I have total green light here. As long as it's between x and c, I can make it anything. Okay. But here's where the story gets a little weird. I want to pick the value of z that maximizes the derivative. What? Yeah, it's true. I want to pick a z that makes this as large as possible. If I can make that blue oval as large as possible, I really am making the entire green rectangle as large as possible. That seems weird since the green rectangle is the error. I would be maximizing the error on purpose, yeah. I want to maximize the derivative, which in turn will maximize the error, which is the exact opposite of everything you'd ever want to do in a science lab. But I want to do that here. Here, in this case, maximizing the error is a positive thing. It's a good thing. And I wrote, it's a conservative approach which allows you to see the worst case scenario. Let me put this into an analogy for you guys, and this is true. I do the budget at home. Not surprisingly, in my family, being the math guy, I get to do the budget every month. And so I've got everything all kind of figured out for the year, and just in case, we have some unexpected, the refrigerator dies. That happened actually last year. Or your lawnmower, catches a bush on fire and explodes. And anyway, just hypothetically. So anyways, you have to budget for things in life. And the biggest thing in my budget that scares the life out of me is not the IRS or the federal taxes or all that. It's the dang gas bill from Dominion, East Ohio. I never know what that thing's going to be. In the summer, when you hardly use any gas at all because you're not running your furnace when it's 85 degrees outside, you open your bill in July and it's like $28. You open the bill in February and it's $228. And I'm like, we've had bills over $300 in certain winters, in certain months. And so it's terrifying. So what I do is when I make my budget out for the family, and it's February, March, winter months, January, I'll make the gas bill $400. I'm probably the only person on the street that opens the gas bill up and goes, yes, because it's only like $300. I feel like I just made $100 I wasn't expecting. I'm like, let's go out to eat tonight. So I purposely overestimated, if you will, maximizing my error in my budget. And that way, I've got the worst case scenario planned for so that I'm happy. Same thing, you go out to eat at a restaurant. You really want to go to this place, but you get in there and there's a line. And you're like, oh man. And they're like, that'll be a 45-minute wait. And you're right on the fence. You're like, should we wait or should we just go? We'll wait. And then 20 minutes later, they're like, loose, party of 6. I'm like, what? Oh, that's awesome. I was expecting 45 minutes. It was only 20, and I'm happy. But let's say that they said, okay, thanks, it'll be a 5-minute wait, and then it was 20. Well, now I'm kind of annoyed, even though I still waited 20 minutes, because they promised me the 5 minutes. I think most places purposely overestimate the wait to make the customers happy. It's like, oh, pleasant surprise. So, long story short, sorry for the babbling, I want to pick a value of z that's going to inflate this as big as I possibly can to make my error as large as I possibly can make it, and that way I can claim, hey, the answer is going to be between this and this, and I won't look like a liar or a fool. My prediction will always be better than or equal to what I claim. Okay, so hopefully that's making a little bit of sense. Let's move on and talk more about the z. So the best way to understand Taylor's theorem is just to do some examples. So it says, use Taylor's theorem to approximate the sine of 0.1. So what I'd like you guys to do right now is go ahead and grab your graphing calculator. Make sure you're in radians. You should be in our class anyway. And just type in sine of 0.1. Hit enter and view the answer. And please don't tell me what it is. I don't want to know. I don't want to spoil a surprise for myself. Besides, you can't tell me what it is because I'm here alone in a room by myself. Great. Okay, now I am going to approximate what's on your screen without being able to see it by using the third degree Taylor polynomial for sine of x. Thank goodness for my laminated sheet. I've got that memorized. I know that the third degree Taylor is right here. I'm circling it in black. And if I wanted to go farther, I could be like plus x to the 5th over 5 factorial. I don't have to build it from scratch. Minus x to the 7th over 7 factorial, etc., etc. Again, I don't need to do that because it just simply said, hey, use the third degree. So I'm like, okay. Keep in mind what I circled. That is approximately equal to sine of x. That's the part of the memorized formula for sine of x. All right, I want sine of 0.1, which means that x is the 0.1. Okay, I can see that. Which means here I want to change the x's to 0.1s each time. Kind of makes sense. All right. Now, nobody ever told me this, but I know that it's centered at 0 as well. Sine and cosine are always centered at 0. If you don't believe me, let me just take you for a quick walk here. Follow me. All right. Do you guys see the parentheses right here? And you're like, what? I'm like, the parentheses. And you're like, I don't see the parentheses. I'm like, exactly. Because they're not there. It's x minus 0 to the 3rd over 3 factorial. This is an x minus 0, but nobody ever writes that. And so it is centered at 0 because of the fact that you don't have parentheses. And people are like, oh, okay, I see it, I get it. Okay, good talk. Okay, so we've established these two pieces of information. All right, I grab my own calculator, I type this in, which isn't all that tough, and I get 0.099833, which I'm going to guess is already remarkably close to what you guys already have on your calculators when you actually typed in sine of 1/10. I have a feeling I'm really close. Not perfect, because again, I only went out to third power. I listed a couple terms. I hardly did any work. How close am I? I'm so glad you asked. I went out to third power with my polynomial, right here, P3. I chopped it right here. The very first thing I left off was the 4th term. Yeah, with a fourth derivative, fourth power, 4 factorial. It's still centered at c, but remember c is 0. So, that's going to be an x minus 0. That is be an x to the fourth. Okay. Yikes. This is the remainder, which is the error. The error is actually going to be less than or equal to the first neglected term, which is what I have in the fraction there inside absolute value. Let me go to another slide and continue my explanation. Hopefully this is not losing anybody quite yet. So my big question as a student and as a teacher was, what's the deal with this z? What's it doing there, and what do I need? What do I care about it? It's a fair question. And again, I go back to my analogy about the gas bill. I want to pick something here that's going to make this derivative as large as possible. In turn, that'll maximize the entire fraction, which will maximize the remainder polynomial, which is the error. So I want to maximize the error. Now here's what gets weird. The original problem, I had you guys type in sine of something on your calculator. So the original function, if I was to build this from scratch, would be y equals sine of x, and I would take 4 derivatives. Here they are. I apologize for my poor notation on the last one. It really should be a raised up fourth power, but all right, anyways, all the derivatives are sine and cosine. The largest that sine and cosine can ever be is positive 1. Therefore, what I'm going to do is I'm going to change that yellow backgrounded oval just into a positive 1. And again, people are going to be like, whoa, wait a second. You just said that the z has to be between c and x. I'm like, yeah, Brooke Taylor said that. Well, doesn't z have to be between 0 and 0.1? Yes, it does. But 1 is not between 0 and 0.1. Yeah, I know. But see, let me back up a slide. Here's the thing, and this is a little unsettling probably for you to hear your teacher say this, but I still don't know what z is. I know it's something between 0 and 0.1. I don't know what it is. I don't care what it is. But whatever it was, I hope I picked the right thing that made that yellow oval as large as possible. In fact, I'll make it even larger. I'll make my gas bill $500 in the budget. That way, when I get my $300 gas bill, I'm like, oh yeah, I made $200. You know what I'm saying? Since the active ingredient and the derivatives are all sines and cosines, the biggest that oval will ever be is 1, regardless of what z is. So I kind of sidestepped the z because I had sines and cosines, which is awesome. Now we're going to see some problems that won't have those, and we'll deal with those when we get to them. But typically, this is what College Board's going to do as well. So I just turned that into a 1. And of course, I've already explained this, but it's in your notes in case you're looking back and like, what was he doing? Okay, I'm trying to make the worst case scenario. Remember from earlier, c was 0 and x was 0.1. So those are going in right now. There's the x, there's the c being the 0. It comes out to this. There's absolute value around it, though that's not really necessary. You're going to get this, 0.5 zeros and a 4. Wow, that's 4 millionths, 4 1/millionths. So the answer that I got just a couple slides ago, by only adding a couple things together on my calculator, was within 4 1/millionths of the correct answer. And actually, that 4 1/millionths is the worst case scenario. I'm even closer than that. Wow, that's awesome. So what I do is I take that answer from earlier, that 0.099833 that I got, and I'm going to go plus or minus 4 1/millionths. So the sign of 0.1 that you guys still have on your calculators, the decimal that I have not seen, I knew that I was close right away with just a really quick Taylor polynomial, third degree. But if I add and subtract 4 1/millionths, I can safely say that my answer is going to be between those two values. And I'm 100% safe and 100% sure that I can make that assertion. Interestingly enough, here's what you guys got. So you can see I did pretty well here using my Taylor polynomials and plugging in the 0.1. Honestly, your calculator is not magic. Your calculator cannot possibly be programmed to accept the sign of 0.1. Instead, what it does is it generates the Taylor series behind the scenes, but it doesn't go just a third power. It probably goes out to maybe 11th, 12th, 13th power, just so that you can have enough digits on the screen that no one will know that it's really faking it. It's using Taylor series behind the scenes. Wow, that's cool. So you can just start to see the power behind some of this, these Taylor and Maclaurin polynomials. In fact, I had a former student of mine from Brecksville that went to Case, and during a summer internship, she was working in a lab down there, and she actually Facebook messaged me. She was so excited. She's like, "Mr. Luce, you're not going to believe this." And I knew this girl real well. She was a student aide for me. We had those at Brecksville, and I knew her family and stuff. So she calls me, and she's like, or gets a hold of me, and she's like, "You're not going to believe this. We're trying to make substances that are wetter than water." And I'm thinking, okay, I didn't know you could do that, but I guess they have less surface tension than water or whatnot. And we're using Taylor's theorem and Taylor polynomials to do this. And I'm like, dang. And of course, I didn't want to talk too much about this because I realized very quickly I was the second smartest person in this conversation. But yeah, she was like, yeah, we use Taylor all the time in the lab. And I was like, that is so cool. So here I'm teaching stuff, and I have no idea some of the far-reaching applications of this, but every graphing calculator ever programmed is just full of this stuff behind the scenes. And I guess so are the labs at Case in some cases, so who knows? So I thought that was kind of cool. All right. Last but not least, in our study of Taylor polynomials, we have a 3-part free response style question, number 8, A, B, and C, and we'll wrap things up. Okay, selected values of the always differentiable function. That's kind of nice. That means that it's never going to have corners or cusps. It has at least 4 derivatives because we see them in the table, but it has derivatives forever. F of x and its first 4 derivatives are increasing between 1 and 3. So you can see that in the table as you head down each row. Regardless of where you're at, the numbers are getting larger as you head from 1 to 2 to 3, no matter which derivative you happen to be on. Okay, so that's what that means. And that could play a part later. Generally, everything that's mentioned has some sort of meaning behind it, so it's good to understand other directions. All right, part A. Write the first degree Taylor polynomial for f about x equals 2. We'll do that first, and then we're going to use our answer to approximate f of 2.1. And finally, a third thing is our approximation greater than or less than the real value of f of 2.1. Explain how we know. Great. Okay, let's get the first degree Taylor polynomial for f. Okay, so this is going to be first degree Taylor, which means we start off with the 0th derivative. In other words, that's just the original, f of x. We're centered at 2, so we have x minus 2 to the 0 over 0 factorial. And since we're going about x equals 2, we're going to use a 2 in here. That's what we do. So that's the 0th term. And now we have the first power term. It's going to be f prime of 2. We're centered at 2, so it's x minus 2 to the first power over 1 factorial. All right, we will clean this up. Let's see what we have. First degree Taylor polynomial. Of course, we know that 0 factorial and 1 factorial are both just 1, so we don't need any fractions anymore. Speaking of 1, x minus 2 to the 0 power is also 1, so that's out. What's f of 2?
If you look at the table, you can see that f of 2 is 5 right here. So that's going to come down. Plus f prime of 2, and f prime of 2 is right next door. That's the 25. So we've got 25 times x minus 2. Okay, that's a perfectly fine answer. You don't have to simplify. If you do, you could say 25x minus 45 as well. But that's, clearly not necessary. All right, let's go with the second part. We want to use this polynomial that we just figured out to approximate f of 2.1. So we're going to put a 2.1 in and see what happens. All right, so in goes the 2.1. This is going to be 0.1, or 1/10, and that's just going to move the decimal point over when you multiply it by 25, so that'll be 2.5. So 5 plus 2.5 is 7.5. So f of 2.1 is about 7.5. All right, that's 2 down, 1 to go. And finally, is this approximation, the 7.5, greater than or less than the real value of f of 2.1? Well, I know that f of x is probably some sort of really wacky, wavy function because it has at least 4 derivatives. In fact, it's always differentiable. But this thing here is a line, which means it's straight. They come together at the point 2,5. You can see that the function goes through 2,5. And if you plug a 2 into here, you can see that that's also going to be 5 plus 0, which is 5. So here's what I'm seeing. I'm seeing a crazy blue function called f of x. I see it going through the point 2,5. I see a red tan line whistling past it, also hitting the point 2,5. They share that point. Right there, they both have a slope of 25. They're both quite steep. I know that the line has a slope of 25 because I can see it in the equation. I know the curve has a slope of 25 because of the chart right there. F prime is the slope. I also see that f of x is concave up because the second derivative is also positive. So I drew it concave up, which means that even though blue and red are equal to each other, they're meeting, they're tangent at the point 2,5, anywhere else, blue is going to be above red if I drew a vertical line. So when I step off and go to 2.1, you can see that the blue answer is going to be higher than the red answer. And the red answer that I got was 7.5. That's this right here. So 7.5 is an underestimate. And I just simply need to say, it says explain how you know. So I will say the approximation is less than f of 2.1. Why? Because f double prime of 2 is positive. It's 20, so curve's concave up. I don't have to mention that it's concave up. That's impressive, but I won't score points. I have to say that the second derivative is positive. Again, I have to show that I realize that the second derivative is what is linked to concavity. All right, so here's my answer. All right, that's part A complete. Let's move ahead to part B. Okay, same chart. This time, I'm asking for the third degree Taylor polynomial about x equals 2. And we already have the first 2 terms, which is cool, so we can just sort of rewrite those. I'm going to dig this out from scratch just so I don't lose anybody. Okay, the third degree. We have the 0th term, which is the 5. Remember, it's actually 5x minus 2 to the 0 power over 0 factorial. Then we have the 25. Again, we're just heading right down this row here. 25. That's x minus 2 to the first power over 1 factorial, which I won't write. Next up, we have the second derivative. That's 20. Taking that from the chart. X minus 2 to the second. So we have second derivative, second power. second factorial, 2 factorial. And we'll go to the third. That's where we get to stop because we want the third degree Taylor polynomial. The third derivative is the 51 that I'm looking at. X minus 2, still centered at 2. This is to the third power and 3 factorial. All right, I'm going to simplify that and box it in. The first two terms can just stay as is. The squared term will cancel and just be a 10 for its coefficient. And then finally, 3 factorial is 6. 51 and 6, you can divide them both by 3. That's going to be a 2. 51 divided by 3, that'll be 17. So 17 halves, or 8.5. And that's x minus 2 to the third power. All right, so that right there is the third degree Taylor polynomial about x equals 2. And we want to use this polynomial to approximate f of 2.1. Well, I probably don't need to tell you that I'm using a calculator here. I'm not going to do this by hand. When I put that in, I got 7.6085. You don't need 4 places. If you always go to 4 places, you'll never be wrong rounding. A head table grader told me that once, because the table graders are trained to just look at the first 3 places. You could truncate, so 7.608, or you can round up to 7.609. If you're a person that struggles with rounding off, just go to 4 places and it won't matter. You'll never be wrong. If you're a fan of exact fractions, which I like fractions, that decimal is the same as 15,217 over 2,000. How about that? So that's also a good answer. All right. And that's part B. All right, one more to go, and we'll be done for the day. Use the Lagrange error bound to show the third degree Taylor polynomial for f about x equals 2, which is the thing that I just wrote, approximates f of 2.1 with an error of less than 2 times 10 to the negative third. 2 times 10 to the negative third. Let's see, 2, 3 places over. I want my error to be less than 0.002, or 2 1,000ths, if you will. Okay, great. Let me go ahead and steal the answer from part B. I'll bring it back over. I guess it's not really stealing since it's mine, so I'm just going to use it again. Let's put the first neglected term on there, the one that I left off. Because since we're talking about the Lagrange error bound, we're going to want to go out one more and see what's there. And that's why they have an extra column in the chart. You're probably wondering about that. We're going to use this 28. It's going to be 28 x minus 2 to the fourth power over 4 factorial. 4 factorial is 24. And before I get too far into this, let's simplify those. You can divide them both by 4. That'll be 7 over 6. I'll just make my life easier down the road, I'm quite sure. Okay, so again, that's the first neglected term. And we know that the error is going to be less than or equal to it. All right, again, we're approximating f of 2.1, so I stick the 2.1 in for the x. And that's what I've got. Let me try to see what this is. I can see the 7/6. I'll make that its own fraction. I can see that inside here, 2.1 minus 2, that's going to be 0.1 or 1/10. And 1/10 to the fourth, 1 times 1 times 1 times 1, that's just 1. 10 to the fourth, 10 times 10 times 10 times 10, that's 10,000. And so you can see that the error is going to be less than or equal to 7 over 6,000. By the way, 7 over 6,000 as a decimal, in case you were wondering, is 0.0001666, and the 6's repeat. So if the error is less than or equal to 0.00016, it's certainly going to be less than 0.002. So, success. We've done it, and we're done with the third and final day of the Taylor polynomials section. Great job, everybody. And until we meet again, have a great afternoon.